We'll be discussing, it's going to be a cursory discussion about conformal bootstrapping. Today, I'll just try to motivate it more. We'll look at a few examples, and hopefully by the end of it, we'll get our hands dirty with some calculations. Not very rigorous ones or in-depth ones. It's just to give you a flavor of the conformal algebra that's going on behind. So I guess to start off with, we can note the observation that drawing upon the ideas of renormalization, QFTs, some of them become scale invariant at large distances. That is, like at long distances, you have low momenta and all the masses are gone. So there are no mass scales in the theory, right? So also let me know what you want me to write down as well. Like these things, if you want me to write down, I can just keep making notes of it, or I can just talk it out.
Sure, like just like a few like quick words, key pointer words could be good enough. Yeah, that's it.
Yeah, QFTs, scale invariant. Yeah, so they become scale invariant at long distances. Yeah, and so if we have a local theory that is scale invariant, right? What happens in most of the cases is that this theory is also part of a larger symmetry. And usually it's also part of the conformal group. So what does conformal group mean? You have scale invariance, at the same time you have rotational invariance, or rather it's angle preserving. Let's just say that. So yeah, these are two facts we need to keep in mind. The third thing is, so for our discussion today, we'll consider only UV complete theories. So what are UV complete theories? You have an RG flow from, let's say, conformal theory that is in the UV to some theory in the IR. If you zoom in to a UV complete theory, the mass scales, they still go to zero. So you're essentially dealing with a very ideal case here. It's very trivial in this sense.
Wait, so I had a small question. When you talk about like some renormalizable QFTs that are scale invariant in long distances, but you still bring up the same notion at local theories. Like, so what sort of observables are you looking at when you bring in something at a local theory scale, which you also claim to have scale invariance?
So by like the entire theory, what do you mean by specific observables?
No, so what I'm trying to understand is like when there's a local theory, it's at the end of the day, you sort of want it to work at any smallest resolution in space. Where again, it's talking about like the UV divergences and the IR divergences. Like, so when you talk about scale invariances, at the end of the day, you say, oh, the IR different divergences are all taken care of, no? That's the long scale part, if I'm not wrong. IR is the long scale part. So IR divergences are taken care of. That's what where scale invariances like normally talk about. But when you say, is that why you brought up UV complete cases? Because there's already an RG flow from UV to IR, or is there like
no, that is the case. But how where this conformal bootstrapping mechanism comes into play is, you don't necessarily need to have UV complete theories. I'll generalize it after that.
Okay.
In the sense, you don't need to have that microscopic description. You can just deal in the CFT, CFT at the CFT level, and that is the power of conformal bootstrapping. And we'll get to that eventually. That was one thing, as I said, many of the CFTs can be described in this way, and so with QFTs, and by understanding the conformal field theories, we essentially are trying to understand the beginning and the end of these flows. Hence, what we are essentially trying to do is we are trying to map out the space of QFTs itself.
Okay.
That is what we're trying to do. Yeah.
So I have a question. So you said that the local large, I think you'll be covering this later, but just for the sake of the question. So you said that the local, so the local theory is scale invariant and at high energies, it also has the conformal symmetry of the conformal group, right?
Usually it does. Usually it
does. Okay.
Usually.
So what?
Not necessarily.
So So one question is how, in what sense are we saying that it's invariant on the conformal group? Are we saying inner products are invariant? Or how are we saying that we're keeping them conformally invariant?
You essentially perform the transformations of the field itself, right? And your operators and your path integrals, all of them.
Okay, I see. Okay.
Yeah. Well, essentially, it comes back to we'll be discussing this correlation functions that are invariant. Of course, the interpretations of each of the correlation functions in terms of path integrals after you shift may be different, but they essentially talk about the same algebra, and the correlation functions is more fundamental to our discussion.
Got it. Okay.
Yeah. Hope that was clear. Yeah. Okay. As an example, we'll just take in 3 dimensions. So we have the 5-4 theory, and we can write down the action of the 5-4 theory as d cubed x. Let me know if I've made a mistake anywhere along the way. I'm prone to making that. If you even remember the action.
Shouldn't it be d4x?
Oh
no, yeah,
I don't think so. Yeah,
it's d3.
Yeah. So here, this is the
unharmonic.
Wait, sorry. When you say d3x, are you implicitly assuming that one of them is time, or is this just spatial?
Without the time, only the space, no?
Yeah, this is action purely spatial. Yeah, we haven't coupled this to any background to bring in ideas of quantum gravity or even flat space time. Nothing is done. It's just simple QFT action.
Got it. Okay.
Yeah.
All right.
Yeah. Okay. So the last term here with the G is the interaction. G is the coupling constant, all of that. And if you see here, it actually has the dimensions of mass. So this theory here, as you know, is free boson in UV. And the canonical dimension of phi is half. So G has mass dimension 1, phi has mass dimension half. So if you go to very high energies, G will effectively become 0.
Wait, can you what is mass dimension exactly? So it's just like m to the power of half in the time. So
in the natural universe.
Whatever in that representation, in the basic
you'll need to do
representation.
A bunch of algebra to but it's
and
essentially
how does it exactly relate? Okay, why are we talking about this?
Yeah, we are talking about this because we see
Easiest
that
way to talk about energy scales.
exactly. Right? Yeah, at high energies, G just goes to zero, effectively zero, and that becomes important because in the IR for generic M we have trivial CFTs, but um, I mean we have like particles have masses, all of that. But we can just integrate it out. That's essentially the point. So, but however, for some special values of m square, we do get a non-trivial CFT. We'll talk about that later. So, when we have, okay, actually, we'll talk about it now. When we have these non-trivial CFTs, right? It's very hard to solve them. Like, for example, if you
Is it because you don't have a cutoff in the sense that they become UV incomplete theories?
Well, this actually, I mean, they're still solvable, but it's very hard in the sense, in the perturbation regime. For example, you have the expansion in terms of G and some X, where X is a length scale or a distance scale. Zooming out to large distances, X goes as 1 over G. X is really greater and not goes as really like X 1 over G. So, and it breaks down our calculations at this point. It's not really perturbative in this sense. But what we can probably do, I mean, is we can probably start out with some, we can work from this dimension, like 4 minus epsilon, where theory is weakly coupled, and do a bunch of computations and then set epsilon equal to 1. And that's how you solve it. But
so you can like, so you're basically like tying up your large dimensions, and you're saying in some scope it like this like forms the closed this thing.
Not sure what you're talking about.
So in the sense, the problem is
Pradyut. I don't think it's that there's really no. So I don't think there really is any physical interpretation to especially this bit, right? Because this is a trick that you see a lot when you're doing any kind of like loop integrals, right? But just because you're going to like 4 minus 2 epsilon dimensions, like doesn't mean like, oh, you're doing some weird compactification thing.
It's not,
like, there's no physical you shouldn't attach any physical reality to it.
It's a mathematical trick.
Exactly. Which means but the other side is like, you have to be very careful about every object that you're dealing with. Like certain algebras just aren't as good in like 4 minus 2 epsilon dimensions than they are in four dimensions, and a bunch of other issues. So that you have to deal with, but there's really nothing physical to it.
Yeah. Hope.
Or you can nicely go from Minkowski space into like normal Euler place.
That's called a Ward rotation or something, right?
Yeah, you can do that and then go back to Minkowski and everything.
No, I think it's Wick rotation.
Wick rotation, not Ward.
Wick rotation. It's Ward identity, which we'll be actually using anyway. It's a nice foreshadowing. Okay, so let's keep this aside for now. Okay, so we have, so we know that it's pretty difficult to deal with this. Now let's take another example. I think, I don't know if we've talked about this in previous Talking Physics podcasts, but 2D and even probably 3D icing models, where you basically have a many body system, you put it on a lattice, and each has, I don't know, if you're considering
spin
like
and stuff.
If you're considering magnetic properties, as you said, you have spins and stuff, and then you have a Hamiltonian and a partition function, all of that that is dependent on the spin. And I think the partition function, if I'm not wrong, has this form where S can either be plus or minus 1. E, actually, I'll write it down like this. Yeah, where S, I, S, J are your, it's either plus or minus 1, depending on the spin. So what this is saying is basically you have you have this lattice, and let's say you take this layer and this layer.
Right? It's like some sort of this thing, right? Input and output.
Yeah,
what goes
yeah,
Okay.
Yeah. I'll actually go on to describe some idea. You can tell me what this reminds you of as well. So you have, let's take this layer and this layer to be constant, and then we perform the summation over the rest of the layers. I mean, there are more here and more here, all around it. Or no, actually, more up and down. Yeah. So yeah, you have this, right? And you get the partition function.
Is this the flux?
Not exactly the flux, but I mean, in the flavor of QFT. Now, let's take this to the continuum limit. What would you essentially get? So this is very discretized. So this essentially...
you're keeping the two layers you marked out, you're keeping those fixed?
Yeah, fixed. Fixed, and then calculating the partition function through the rest.
Is it something like you're defining that to be a ground state?
Not exactly. So I'll just tell you what I was getting at was this is sort of like a discrete version of a path integral, if you think about it.
Okay.
Yeah. So
that's actually pretty neat. Yeah.
No, isn't that kind of like, isn't that what was kind of the point of like statistical field theory, kind of like the fact that they realized that like this? Yeah. Okay.
Exactly. Yeah. Actually, I was reading up. Okay, this is a slight aside again, but I was reading up on this, dynamics in imaginary time is statistical mechanics in real time direction when you're considering Wick rotations and stuff, and when you're when the time is imaginary, quantum mechanics is essentially statistical mechanics when time is imaginary, and vice versa. And that's why the whole idea of Wick rotation works and all of that. I don't know why what Charnil said reminded me of that, but that is a cool idea to explore as well. The idea of Wick rotations. It's really
that
fascinating.
Actually makes a lot of sense.
Yeah.
It's one of those things that should
yeah.
It seems like one of those things that should be intuitively obvious, but just like you don't kind of hit on it.
Yeah, and you know why this is? Because you have that thermal function, partition function or whatever, e to the power minus beta h.
Right. Yeah.
Now, if you consider beta to be it, it's just evolution in like quantum mechanics.
Wait 1 second. Like I think, okay, so if in mathematically speaking, like if you have some sort of a discretized theory, that is like quantum theory, whereas if you have some sort of a continuum based theory, that is statistical mechanics. So if you like, okay, so what I'm thinking of is like, if you say the jump between two integers like makes a discrete theory, then that jump between the two integers can be recorded into the like a complex plane where like all the rational numbers between the two integers can be like seen as something complex, and then you just jump to the discrete. In the sense that what your normal like the factorial, the gamma function or anything like talks about, right? So you have like the jump between like point like function to be given by a complex.
I know what you're talking about, and that is actually a mathematically valid idea. I don't know if it's used anywhere in physics, but this, rather than commenting on the discreteness or continuity of theories in general, it's more a commentary on this Wick rotation. Like, what does it mean to work in Euclidean signature and Lorentzian signature? Why are they equivalent?
Yeah, but like, how does that translate? Like, what does imaginary time like correspond to, or like, what does real time correspond to?
I mean, imaginary time, you're working. So where do you use imaginary time? Like in the evolution operator, all of that. So
Yeah.
what is it actually evolving? You are actually
Yeah, so
evolving
if we can,
in the Hilbert space.
Typically, you don't really use imaginary time per se, but it just picks up phase of it. Just the eye is there just to see the phase.
exactly. So what I'm trying
There's
to
a
say
small
is like,
caveat. No. There's a small caveat here though, because it seems like you don't really use imaginary time as much as in QFTs, but in GR and especially like when you're discussing black holes, I know Hawking used a lot of imaginary time. Like I think he pioneered what is called imaginary time formalism to deal with gravitating systems, to like study relativity in a mathematically consistent framework.
And a fun fact about that, he while considering actually not just imaginary time but the metric itself to be imaginary, he was able to rederive the properties of I think a Kerr black hole if it as the same as when using real time. So there's a much
there's like already some consistency there then.
Already some consistency there. Yeah. That's
coming
what Sharnil was talking about, I presume.
Coming back to like when Rahul, you said like it picks up the phase, like it again reminds, like I don't know, like I somehow like find it like very connected to the concept of like discrete integers, and then you have like some sort of continuum between them, and in order to bridge across that continuum you need some sort of a complex or like the evolution operator or like something that picks up a phase. And I don't know, I just like it's just something that there we can just think about it in the back of my mind.
Think about it, and probably we can discuss it over the next call, because right now I still don't see it.
One more nice interesting thing to see if there would be a connection is if we could take out if there were any observables which had time without an exponent in it, and see if imaginary time in there brings in the same statmech relations. That would pretty much like solve the whole confusion right now, I feel.
Has any effort been put in that direction? I feel like that. I don't know. Yeah, I mean, if you find something interesting, I'll also look for it.
Yeah,
that is an interesting thing that we could probably discuss.
I mean, just at the very face of it, all it is a coordinate transformation. That's all you're doing.
Yeah.
So like, as long as you deal with objects, as long as you consistently make definitions, things should be fine. But then like this again is like a very intuitive and hand wavy statement. So don't just take it with a grain of salt, I guess.
Yeah. Okay, that was a nice aside. Coming back to this. So when you fix the two layers and you compute this partition function, what it actually computes is transition amplitudes from one set of spins to the other. That is essentially what it's giving you. Now, the very interesting thing about this is in the continuum limit, this actually becomes a QFT, this Ising model. And for some special value of J, right, it actually becomes a non-trivial conformal field theory. And what's even more interesting is it is the same as the 5-4 theory that we discussed before in the continuum limit. And we can maybe go through that calculation someday. Probably
the three-dimensional 5-4 theory?
Yeah, the three-dimensional 5-4 theory, if you consider the 3D lattice.
So where exactly is the coupling thing coming from here in this case?
It was J.
J is the sort of G counterpart.
Yeah, J is the G counterpart here.
And
So,
so I'm also
where,
assuming
where,
since that's
where,
the only term, J also gives you masses.
yeah, that's what I was going to go for. Yes, yeah.
Yeah. Probably we'll have to do the calculation to see how we can do it, but I suspect so. Yeah.
Interesting.
Yeah. Yeah, this is an interesting thing. Yeah, we'll come to this later. If
Okay, I'm
yeah,
just gonna one more question before we move on. So one
yeah,
thing that's kind of been bothering me about this entire thing is that the FIFO thing just set up in D equals 3, right? With no time.
yeah,
And this
yeah,
also is just JSISG, just coupling a bunch of spins in the lattice, right?
yeah, yeah,
So okay, it makes sense that both the theories are essentially non-dynamical because there
yeah,
is no time derivative.
yeah.
So what does that mean in a physics context? Like what do these excited modes correspond to if there is no dynamics?
So the thing is, over here, I mean, we had the action previously, and this, which essentially gives you the dynamics, but not time dependent in a way. And that's where your path integral picture comes in, where you slice up time and
Okay.
do all
So this,
So
this,
I
this,
guess it's more like
in a sense,
the speed doesn't matter, but only the relative distances matter, rather
yeah,
like
Yeah.
yeah,
Oh, so something like spin waves and stuff, because everything is
hmm,
in the
hmm,
same
hmm, hmm,
spot essentially, but like there's still a long range coupling of properties.
yeah,
I see.
so
Okay.
okay, so it's like okay. Another thing is like it's like the boundary conditions are not fixed. If you just talk about a free field theory, and you just need like you just have the general like structure of like relation or the algebra like can you
mm,
call it algebra like between the variables
mm,
in some sense or like some sort of a relation between the variables. Yeah.
yeah,
Okay.
yeah, yeah. Yeah. I
Yes.
guess we'll move on. So this brings us to the essential motivation of the bootstrap. That is, there is an idea called critical universality, or it's even called duality. So
wait, sorry to cut you off. But
yeah.
like, could you just share that part where the icing thing becomes your normal P4, Phi4 later?
Oh yeah. I'll
Yeah,
definitely do that, and we can even
yeah.
probably talk about
Sit
it on
until.
one of our calls as well.
That
Um,
yeah, that actually seems very interesting. That's
yeah,
mm,
this is all really interesting. Yeah. I was actually looking for more resources as well, um, describing how, like, uh, actually, I'll get to that part. Then I'll tell you what.
yeah. If there are no good enough resources, then I guess we could understand it and put one of our own.
Yeah, exactly.
If
That's
it's
what I
not.
was talking about.
Mm.
But yeah, so then we have the motivation. So we have the precursor to the motivation, and the motivation is essentially this idea called critical universality, uh, or sometimes it's also referred to as a duality. I don't know in which context though. Yeah, but so we have some like multiple microscopic systems that flow to the same conformal field theory in IR. By flow, I mean RG flow. And this same CFT actually also shows up for water during phase transition, and magnets, ferromagnetism, and that's why you have all the icing model stuff flowing to the same 5-4 theory. And it also even comes up in SU2 Yang mills. So core confinement, all of that, and phase transitions there. So it's really profound, as we can see from this. So instead of really depending on the microscopic description, we'll see if we can use some effective field theory techniques. That is, just deal with the CFT itself. Because there are times when you can't really find out the Lagrangian for the microscopic theory. This regularly happens, for example, in string theory. For example, I haven't personally gone deeper into this, but the M5 branes, effective field theory of M5 branes, you can't calculate the Lagrangian. But what you can do is you can consider the flow to some CFT in the IR and manipulate that CFT. Again, you're using effective field theory techniques. So, yeah.
Okay. So in this sense, like the visual picture that I get is like your at extreme conditions or asymptotic conditions, your like expectations values or like something, the results basically remain the same despite the underlying theory that you're trying to talk about. And in some cases, your underlying theory cannot be like expressed in terms of a rational Lagrangian or like something like that. So in the sense that there is some sort of a like I wouldn't call it to like a cage invariance per se, but like there is some sort of like a abstractness or some sort of an invariance in choosing the theories between the asymptotes, and therefore you just like talk like about stuff at the asymptotic limits and then like project it back or something.
Is it more about like, is it more like an effective field theory?
Yeah, it is effective field theory.
Okay.
Yeah, same techniques here. Yeah. And I'll be careful using the word asymptotic, but yeah, I know what you're trying to say. And yeah, that's essentially what we're trying to do here. So what we'll try to do is we'll determine the full consequences of symmetries and impose some consistency conditions. This will actually result in a lot of non-perturbative information, so constraining sometimes that we can completely solve the theory without the use of perturbative techniques. And this is widely known to work in 2D. But I think for the past 10 years, there's so conformal bootstrapping was done in the 70s, and then it kind of died down. And now there has been a resurgence because people have found out that it's not only 2D, we can actually do this in higher dimensions as well.
Wait, so I have like a small question. When you say it's already, you're sort of looking at very extreme cases to solve something.
At IR, yeah.
At IR, when you say you're looking at theories, generally you use it for theories where you can't really write down the Lagrangians quite so easily. But what does it mean by saying where you can solve the theory without actually a lot of trouble? When you can't really completely understand the Lagrangian normally, but you're only solving it for extreme cases. But
the correlation.
Am I connecting dots?
And, yeah, the correlation functions and like operator insertions at that level that has like different path integral descriptions. They all make sense.
Because it still to me, it still is a little confusing because at the end of the day, you're looking at the IR scale. And when you look at it in that time, so maybe the microscopics are lost. So again, it's more of an effective description, like the same thing of effective field theory. Right?
So over there, what essentially ends up happening is to recover the UV theory back, right? We add in some of the irrelevant operators that go to zero to the CFT.
Okay.
That's how you recover the UV theory back. If that makes sense.
That's interesting.
Yeah.
I guess if you could, when you get into more details, it will be more clear for us to understand.
I don't know if I'll be able to get into it today, but yeah, hopefully sometime soon. Or we can have this as like a really multi-part talk.
That should work too,
yeah. Okay. Now we actually, I think I've motivated it enough, and we'll actually start getting our hands a bit dirty, not too much. Okay, so now the first thing is, so what did I say? We try to look at the symmetries and impose some consistency conditions, and that's how we try to arrive at the solutions for the theory. So I guess step one is look at symmetries in these theories. So for a local QFT, we can have a look at the stress tensor. So you know that the QFT must have a conserved stress tensor. What does that mean? It means yeah,
zero, yeah.
the divergence is zero.
So in the sense, okay. So in the sense, there is some sort of a boundary, basically.
I mean, yeah.
Or like, it's like a closed system, essentially.
I mean, yeah, I guess it is, yeah. But yeah, you can say that. Yeah, you can say that, I think, yeah. And yeah, so, but this is essentially an operator equation. So you have to be very careful with operator insertions and all of that. As long as it doesn't, within the path integral or the correlation function, if it, as long as it doesn't coincide with any of the operator insertions, this equation should hold true, right?
You basically need to keep track of phase in the sense.
Phase, not exactly phase, no.
Okay.
Yeah. Again, yeah, you keep throwing things at me. I'm trying hard to connect it. Yeah. Yeah, but yeah, I mean, if I don't see something, you can explain it to me. But yeah. So we can write the word identity for this, since it's the operator equation. And so word identity, if you remember from your QFT classes, it's a statement that's derived based upon global symmetries of the theory. It's very interesting because we are considering a local QFT here, but they should still hold true. So you have this, and then let's say you have a bunch of operators being inserted, right? And I'll give a more visual picture of this later on. Like,
wait, so are these operators space dependent?
Yeah.
Like no, I'm not, like, let me rephrase that. Are these operators specified on a particular point in space, or rather, like, are they well defined everywhere? Or more like, are you looking at values of these operators only at certain points?
Yeah, I'm looking at these. Like, these operators are, so you have some initial state, and then like you have operator insertion at one point, then the other point, and so on. So this appears within the path integral as well, right?
Your theta 1 is basically your operator for x1, and then your theta m is your operator for xm.
Yeah. And so what the word identity actually gives is this.
What are these operators? Like, what do they, like, any random operator you can just choose. So they don't even have to be the same operator also.
Yeah, they can be different.
Okay. All right.
So they're like you're like filling some information, missing information with these operators, sort of.
Yeah. With the transition in states and stuff. Yeah. You can consider that. So you have this for the word identity. Where theta are some operators, and so yeah, again, t should not be at any of these points because of the operator equation condition. Then you naturally have that the divergence is zero. So another thing that can be done is when you have the word identity like this, we can pick some open ball. This is where the geometric picture comes in. That encloses some operator insertions. So let's say this is the region that we are dealing with in now space, yeah, and you have some random operator insertions, right? O1, O2, O3 in x1, x2, x3. So let's take we pick a ball that encloses some of the operators, right? Operator insertions. Let the boundary of this ball be called sigma. I also, I'll probably find a good place to stop at. This is not really a good place to stop, so I'll just continue. So you have this, and so we integrate this previous equation over this ball. And what do we get? Is mu so you have theta 2 and theta 3 here, but in reality, this is just an example, so we can have more here. And this will be so I should belong to B, and you have do I mu, and essentially
you have don't you have like m word identities for like m operators, because like you can isolate each single point and then like group the other points together?
Yeah, you can, but we are just doing this for team mu. That's it.
Okay.
Yeah, that reminds me of like what Pradyut just said, was like reminds me of this that stereographic projection or something. It sort of like brings in infinity, like a 2D plane from minus infinity to plus infinity, balls it up into a sphere and makes everything look like one point. So you're going to take all the points like your theta 2, theta 3 till theta m as consider as one point and put them all into, make that instead of like a ball of a surface, you could just look at it as a point and then keep on reimposing the same situation over and over again.
Right. Yeah. Yeah. I think I get what you're trying to say. Yeah.
Yeah, I don't think it were really useful, whatever I said, but it's something that reminded me of what you said.
Yeah. Okay. So where was I? Okay. So we have this. Let's keep this. And let's also consider this. Mu, team mu. I don't know if this is familiar to you already. If not, I'll reveal it to you later what this is. I'll name this as some other operator, P mu.
Isn't that just the momentum operator?
Yeah, it's just the momentum. So it's, well, we don't know that exactly now. Sort of.
But we do slightly.
Yeah. Yeah.
You called it P. It has the momentum. There is no other possibility.
Yeah. I mean,
because if it were with respect to like time, then I would say like it were energy, but still there is this, we are looking at non-dynamical systems.
Yeah.
Again, momentum also doesn't make sense again in this case. No.
Yeah. So this operator is actually called a topological surface operator, because coming back to this picture, now let's say that we have this, and there are different operators.
Sorry, is this kind of like you're looking at the flux of the energy momentum tensor through a surface?
Yeah, you can say that.
Yeah,
but
well, sorry,
go ahead. Yeah,
no, go ahead.
no, since this is like This is a stress energy tensor operator here. There is not really a flux going anywhere.
I see. Okay.
Yeah. But I don't know if that can be a valid description. I'll have to think about it.
So
Yeah,
another
sure.
question is, when you're talking about the expectation values of these things, like expectation over what?
What do you mean? These are
Like,
correlation functions.
exactly. So like when you write these brackets at the
Oh
end of
yeah,
the day, it's with,
some
are you
initial
talking about like its ground state or current initial state, or like
initial state? Some initial state doesn't really matter. You have some initial state and final state, and this is where actually the time part is coming in, if you did notice. Because of the correlation function that comes in.
Wait, I don't get that.
yeah, same.
So you have initial state at a particular time, and so these operator insertions, so these can be your time slices. I'm just picking some random direction.
Oh, I see. I see. Okay, that makes sense.
Okay.
I mean, correlation function is just that, right?
Right.
You like
Right, so
slightly
it's
scroll down a little bit.
Yeah.
Yeah, just the wait, hold on.
Also, I don't know if these are good notes. No pun intended.
So basically, from what I get from what you said, is basically the thetas are the ones that hold the time information, and how evolution is sort of embedded within these thetas. Time evolution is sort of embedded within these thetas.
No, they're not embedded within the thetas. These thetas are just insertions that tell you how the state changes. The correlation function is what you're talking about.
So thetas are just basically like, okay, so
Some
let me
operator.
let me just clarify, like, is theta basically just like why you correlate it with your momentum operators? Essentially it is some sort of a tangent, like in the sense it's a tangent operator in the sense that it is tangential to one point, which means that it connects from one point to the next in some sort of a way.
I mean, there's no connection to the momentum. These thetas, yeah, they do that. They keep changing the state, so you get the overall overlap essentially in between initial and final states. They help in explaining that. But I'm bringing up momentum for another reason here.
Okay.
So like following up on what you guys just discussed, so what would it like? What exactly does having that open ball with excluding theta one mean in this case?
So
are you like starting at a different time, or are you starting at like a different slice or something like that?
Yeah, it's a spatial slice, or it's a ball in space essentially.
No, since you said the thetas are the ones that you're fitting in as slices to talk about, to bring in time into the picture, right? So when you're excluding, like say in the figure that you drew, theta one is
it's a correlation function.
So you to simplify this, you could look at all the theta 1, theta 2, theta 3 are as like let's say three, like if you only include three of these operators, we could look at them as three different particles at spaced so and so distance away from each other, like sort of looking at it in a different perspective, right? So when you're including, so when you're writing only theta 2, theta 2 and theta 3, you're basically finding the correlation between just these 2 points without the influence of the first particle.
Yeah.
Right. So when you could look at this problem this way, I don't understand where the time slice comes into picture.
Isn't it like okay? I think I might have agreed that. So isn't it like like you said here, you're freezing at a moment in time, and you're like, this is my past and this is my future, so or like something like that. So you can correspond to like some process transition happening as like this is my past and this is my future, and like what would my amplitudes
It
of the
is,
correlation
yeah,
between the past and the future
yeah.
be?
It is essentially we are shifting between the correlation picture and the path integral picture. That is what we are evoking. What
But
Pradyot
at the end of the day, they're still both of them are still talking about the same thing now.
Yeah.
So
Yeah.
Okay.
So you're just considering a different time slice at that moment. Different time slices at that point when you're not considering the first operator insertion or what happened before that.
So I guess the funny part is like the correlation is basically the particle with itself. It's in the past and it's in the future. So I
Yeah,
guess
yeah,
that's where you're.
yeah,
That's
yeah,
that's pretty neat.
yeah, yeah, exactly. That's what I'm trying to say here. Okay, coming back to this. So this is a topological surface operator. So I'll explain what that means. So what that is if you compute the word identity with inserting this operator here into the correlation function, then the result is the same with any other surface enclosing the same operators. So what I mean by that is this actually comes into quantization as well. So let's say there are some there are some operators here, and now what I'm doing is I insert this is my surface here. It's closed. Well, it can be asymptotically closed as well. So you have P sigma here, P mu sigma. Now, if I consider another surface, P sigma, prime, they would
So
yield all the same word identities or
so
expectation values or whatever, because
you
we have not interacted with the operator insertions yet.
So are you basically like transforming your space
It's
into from like are you transforming your space from talking about your x like the space in terms of x or the distance or like space time to the space in
surfaces
terms of
itself.
momentum operators?
Yeah, you can probably say
You
that.
can are you transforming that space like that, and then
I'm not
you'll actually
transforming the
find
space.
like
Um, uh,
level
I'm not.
sets.
Yeah, I'm not transforming the space. So these operators here, like this, which are surface dependent, are the same for any point on that surface.
Okay, based on like okay, fine.
Yeah,
It's like
and
a
what? Yeah, and if you deform this, it still remains the same. And these are called topological surface operators because they only vary with the varying in topology. So we can move sigma freely as long as we don't cross paths. This actually follows from path integrals again. If you consider the path integrals for this picture, it's it's the same thing.
That again is like sort of talking about another symmetry concept. It's actually pretty
yeah.
So it's like it's basically like saying until the momentum actually changes or until some variable changes, it doesn't change, or it is.
Or more like if the body doesn't, if the object doesn't move, then till that point it's like everything is
It doesn't
conserved. So you
move.
can start picking your clock once you come across one of the thetas.
Yeah. So these essentially correspond to symmetries, these topological surface operators. Yeah. And yeah, you can see how you got the topological surface operators is. So we can find others like this. I think that is a good place to stop for today. We can continue. Yeah. Let alone a 2-part talk. This will be a 3 or 4-part talk. Yeah, but it's good. It's good that we have these digressions. But I'll just pause the recording.
More things to meditate upon. Yeah.
Yeah.